Welcome back, everyone. So, sorry for missing a day yesterday of recording, but I was a little busy with, again, all the work that I've been getting, and simply because it was a holiday as well. So today we are going to be, it's a little bit of a continuation of the end of the last video. So I just want to briefly take a look at what we did at the end of the last video. Which page was that? Fairly certain. Here it was. So here we attempted to define a set where we multiply some constant c by some vector v such that c is actually constant that is a member of the reals, right? So we defined our set in this way, and we said that whatever this v is, whatever its magnitude is, in this case we're saying it's a position vector, that any constant multiplied by c in its standard position, that's our specification, it can all be graphed through this line. So in essence, it's kind of like this equation: y equals kx plus b, right? In essence, that's really what it is. And you might ask why it has to be so complicated, right? Y equals mx or kx plus b is much more simple than this obsolete or obscure set definition that I've given. Well, the reason this is so useful is because it can be used in 3 dimensions, it can be used in 4 dimensions, etc., etc. So that's why today we are going to be covering. I'm going to get some papers ready. Going to be covering parametric representations. I'm going to shorten that with the abbreviation rep of lines in n dimensions. And meaning any dimension, like 2 dimensions, 3 dimensions, 4 dimensions, etc. And dimensions. This is the key. Okay. So why don't we start off with looking at that set definition again. I'm gonna write it down here. So we thought of a set where we had any constant. In this case, I want to represent it as this because it's going to make sense, because obviously this stands for scalar. A scalar represents scaling this vector, multiplied by a vector v, right? Such that this number, not to be confused with the set itself, is a member of the reals, right? So let's pick out a value for this vector v. Pick out something that's not too big of a number, since I'm graphing this on paper and I don't want it to be too difficult. So let's say we have -1, 6. Okay. That's our vector v. So let's graph that real quick. And actually, we can first rewrite this set definition quickly, since we've picked out a vector for vector v in this case. So some scalar times vector -1, 6, such that scalars are a member of the reals, right? Right. Okay. So we've rewritten it in such a way. So let's graph it. So -1, and then 1, 2, 3, 4, 5, 6. So that is our position vector, right? This and the head of this vector, or this line, or this arrow, represents the position or the magnitude of this vector here. So this is our vector v, right? And now what if we scale this by any scalar s, right? So we could scale it by 2. I discussed this in the last video, the previous video, so I recommend checking that out. I'm not gonna go into too much detail, but let's, for example, scale it by 0.5. 0.5 times v, right? So that's just half of all the coordinates here, and that would end up somewhere in the middle here, right? That would be our, that would be our v prime, right? It went through some transformation, and I'll get to that later on. All right, so that's just a brief example. So now we could multiply that by negative sign as well, right? And that would just make it collinear with, this line here, right? And that would be v prime prime, and so on. And eventually this creates a line, and this line graphs all, this line goes out infinitely, so on and so forth, right? And that gives you all the that gives you all the solutions for the prime number, the v primes, v primes of this basis v, vector v, right? So let's continue. So now let's get on to a few more complicated topics here. 6 minutes, got it. Let's start off in this case by graphing something. And we're going to graph 2 new points, v1, v2. So let's set v1 equal to 4, -2. Okay, so 1, 2, 3, 4. 1, 2. So this is our v1, vector 1. Then v2. Just going to position this a little better. v2 is equivalent to, I don't know. Oh, and by the way, we're starting this all from standard position or from 0, 0. Let's say 3, +2. So 3 and then up 2. Right, and that's our v2. And what I'm trying to say is, how could we describe a secant line that passes through both of these points, right? Just like so. How could we define such a line through our definition of sets, right? And normally what you would do in Algebra 1 or Algebra 2 is you would line these, the coordinate points of this up and find the slope and then substitute that in, etc., etc. And that would be easy, fine and dandy, right? But today we're working with set definitions, right? So we're not going to worry about that for the time being, even though it seems easier, but in essence you can't apply that in 3 dimensions or 4 dimensions or even 5 dimensions of space, right? So we can start off by, finding the difference of any of these 2 points, right? So let's say if we did v2 minus v1, that would give us, and I described this in more detail last time, that would give us this over here, right? The difference, what is left over. This is the vector that's left over after this difference occurs, right? And it actually might be greater, right? Because we have a negative. Anyway, I'm not going to get to that. We went to the difference of vectors in the past, so yeah. So we can start off by this, and again, since we've gone to this, we've gone to vector that's aligned with this line here. And all we have to do now is scale this by some parameter t, some random parameter t, right? Or s, we could use any value, but this is trying to look familiar from when you learn parameters, where t can be any scalar constant, some random scalar constant, right? And this seems like it's all fine and dandy, right? This seems to work. But in reality, if you were to plot the same vector or the same vector that is the difference of these two vectors. If you were to plot that here, so let's see where that goes. So it starts here, moves 1, so that would be, so it would move back 1, it would go up 4. So that would be this guy. All right, I scaled that up a bit, but it's basically what it is, right? So this is obviously an equivalent way of defining the difference of these two vectors here, right? But obviously this may be a parallel line definition here if you multiply this by any parameter, but we want a definition for this line, right? So the solution to this would be by adding either vector v2 or v1, since this is directly parallel and it's from the standard position. So as a result, adding this to any of these scaled points with regards to this vector here that you get over here, you get some point on this line, right? So let's rewrite this now. So now let's write L for line, I guess, and then set our parameters here, and then here's one of the options. I'll give you guys one of the options here. So let's say vector 2 plus some parameter t times the difference of v2 and v1 such that this parameter t is a member of the reals. Here's one of the options, right? I'd have to split this up into 2 videos. So, or L is equal to v1, vector 1, plus t times vector 2 minus vector 1, such that t is the member of the reals. Right? So these are 2 equivalent ways of defining this, right? Because if you can tell that this is from standard position and this is the magnitude. So that just gives you any point on this line here that we want to define. So look, we've just defined a line, and this is really useful for multi-dimensional things, right? And now, since we have these 2 points already, v1 is equal to this, and v2 is equal to this, we can try plugging this into this definition of a line, per se. So L is equal to, and we're running out of space here. I'll get a new piece of paper. Oh, that was close. So L is equal to v2. We'll use v2 as an example here. I could use v1 as well, but I'll use v2. So v2, I'm just copying down v2 here, plus the difference of v2 and v1. No, I'll distribute the -1 here. So plus, I know this is difference, but as we saw in the previous video, we could just distribute the -1 here. So -4 and 2, right? Such that, oh, I forgot the parameter t, such that t is a member of the reals. Yep, and that is our I'm going to simplify it. Just add these 2 together. Also, that's a long L. So 3, 2, plus t times, okay, so 3 minus -4, that's 3 plus 4, which is 7, and then 2 plus 2 is 4. Oh wait, no, we're not subtracting, we're adding, my bad. So this is -1, and then 4. right? Because we went to back 1 and we went up 4. So that makes sense. Plus t times this, right? Now we just write our t. Our parameter t is member of the reals. So you might be thinking, how do we put this into a parametric, two parametric equations, since we're dealing with 2 dimensions, 3 dimensions, but you get the idea. Okay, I'm gonna finish this video in a bit. Well, basically we can say that this is our x-coordinate, and this is also our x-coordinate. These are our y components, right? So now we can say that our line can be defined using these equations. So 3, our constant 3, plus -1 times x, and our second equation is 2 plus, my bad, this is supposed to be t, we're thinking in terms of t, right? Plus 4t. And this is the standard parametric equation that we've just derived from using our set definitions in linear algebra. So hopefully you guys learned something today. Hope you enjoyed the video, and see you in the next few videos. Bye-bye.